Thanks for the introduction, and good afternoon, everyone. Today, I'm Ryong Chen. I'm presenting our work called StarLego, enabling custom physical layer as well as over community devices. This is a joint work with me and my advisor, Wei Gao from University of Pittsburgh. So we are currently at a fast-evolving wireless technology era. So for the cellular network from 5G to 2G, we have experienced 1,000 times data rate increase. And for Wi-Fi, from currently AX to the B standard, 20 years ago, where the user base has been increased significantly. And for the Bluetooth, from Bluetooth 5.0 to 2.0, the power consumption is significantly reduced and the data rate is also increased. But during this upgrading process, it did leave us many legacy devices. This is the big problem here is those legacy devices cannot enjoy the benefit from the new standards. So why those old devices cannot enjoy? Because such an incompatible PHY-Layer hardware design. So given a mobile phone like 20 years ago, it's using a very old hardware. Imagine it as a monkey. So it can only speak whatever monkey can speak. And then we have the new hardware, which is latest, like fancy iPhone 11, that think about it as an Einstein, that it can tell you how quantum physics works. So when Albert Einstein wants to tell the monkey, okay, how does the physics work? So we have this atom, whatever. The monkey cannot understand at all. Vice versa, if the monkey wants to tell the Einstein, I have a banana, Einstein basically cannot understand too. So the old hardware basically cannot produce, transmit, or decode any new signals. So you may say, okay, I just go ahead and upgrade. So you have a very lousy G network at your home, and you can't stand it. You want the Wi-Fi 6, and you go to Walmart, and you find the latest version of router costs like $300, but you don't have that much money in your wallet. You still, so you cannot upgrade, so you can still keep at the G standard network because the cost is too high. So is there any way that we can bypass such gap between the old and new devices? So right here, could we use the old devices to emulate the new signal that the new devices can successfully receive and decode that signal? There's a possibility. So given a scenario where the old devices and new devices, they have completely incompatible physical layer. Before, because the signal pattern is completely different, basically the new device cannot recognize the signal from the old devices, and either they have to drop the frame or they have a larger amount of decode error. So instead, we can manipulate the MAC payload at the older devices to create a similar or exactly same signal pattern as the new devices to allow the new device to decode and then correctly the signal transmitted from the old devices. By doing so, we are able to bridge the gap and make these two physical layers somehow compatible. So before we go into the details, we have to first understand how does the time domain signal works. So we can represent any time domain signal by its amplitude and phase. So here, example, we have four segments of the time domain signal with the same amplitude and different phases. And another way to represent it is using the concentration points. So these four represent four individual concentration points on a concentration diagram. Each of them has a unique amplitude and phase corresponding to the time domain signal. So if we want a new time domain signal here, so we change its pattern, correspondingly, the pattern will change on the concentration point. So right here, could we just change the concentration point by manipulating them and to emulate any new time domain signal? So there's a possibility, right? But you may ask, if we only have one signal, we only have one amplitude and phase, how can we create or how do we move those concentration points? So right here, if we involve two signals, we will be able to do it. So if we have two signals, the signal will be shown as here. And as the concentration point, you have two old signals from here. And then when they mixed, they create a new amplitude and phase, right? So by doing so, imagine you have a lot of known concentration points. You will be able to create thousands, maybe a lot of new constellation point on the constellation diagram. So in order to study that, exactly how much we can achieve on the new constellation point we can emulate. We studied the constellation point to be created with respect to the number of TX antennas and the modulation scheme. As you can see here, if the TX antenna increase, all the modulation scheme increases, the number of constellation points can be emulated is significantly increased. So based on such insight, we propose our design, which is called StarLego, which is an emulated arbitrary time domain signal by mixing multiple MIMO signal streams together. So this design is completely, we don't need any physical layer modification. We just simply manipulate a MAC payload. We create a we design the standard time domain signal from the MIMO streams. So when they combine in the air, we create the desired time domain signal we want. And then such desired time domain signal will be correctly decoded by the new devices as the designed payload. So imagine that you have a castle you want to build, right? So that's your desired, you want to build something like this. And then your standard constellation, standard time domain signal will be your base block to build the castle. So that's why we name it as a StarLego. So how do we exactly to control the MAC payload? This is a key component here. So given a non-time domain signal, we can map it to the design constellation point. And then we unmix them to the standard constellation point. And then we reversely doing the physical layer operation. So basically this reverse physical layer operation is just reverse engineering of current physical layer approach, physical layer implementation to get the MAC payload. So here example of how does this reverse work. Given a Wi-Fi example, we have MAC payload and then it will be scrambled, it will be encoded, it will be interleaved, and then modulated to the standard constellation point. So reversely, we just take the standard constellation point from the unmixed signal, and then we demodulate them, and we de-interleave, decode, and descramble them, and we combine them together. We can acquire the MAC payload for emulation. So this is relatively not hard, right? So after acquired those MAC payload, we try to test the performance of our StarLego. First, we know we need to create a new constellation point. How exactly StarLego perform when they are creating new constellation point? So given a 2TX with QPSK, we can emulate a 9 QAM. And then 2 times 16 QAM, we can emulate a 49 QAM. From these two figures, you will be able to see that this, the created constellation point basically match the theoretical constellation point what we want with a very, very low bit error. And then we need to pick up a showcase to examine how exactly StarLego perform when we're trying to emulate a new custom physical layer operation. So we pick out Emily. This is a paper from 2011 which won the Best Paper Award at the Mobicom. So what Emily does is append the custom CGS to a preamble, to a standard Wi-Fi frame before the preamble to allow the basically the RX to save power when idle listening. So how does Emily detect such CGS? With they just use autocorrelation, which shows the similarity between the perfect CGS and the received signal. So if the signal is very similar in time domain, it will show a high correlation, and then if it's not, it will show a low correlation. So before we go into the result, we have to set up our system. So in order to create an emulated Emily frame here, we need to guarantee that the frame started before the CGS. However, and which means that we need to make this part recognized as a channel noise. However, because of the existence of standard preamble, if they are perfectly matched, there will still be a standard preamble, right? They will not be recognized as channel noise. But there's a good thing is, in a Wi-Fi standard, there's a plug-in ceiling shift, which is predefined in the standard, which means that this TX2 standard preamble, this frame has a slightly shift compared to a TX1. By doing so, when the RX is receiving, this part of standard preamble will be recognized as channel noise. Then you'll be asking, okay, because there's a shift, how do you guarantee that the later parts The payload we want to emulate, the only thing we can control is perfectly synchronized. Because this sitting shift is predefined, so we know exactly how long it is. We can basically just play some dummy bits to compensate that shift to make that the rest of the data payload we can control to be perfectly synchronized. So at the receiver side, you're showing a perfect correlation between showing a perfect emulation. So here's our result. So basically, first we need to detect the CGS, of course. This is a key for the emulate. So as you show from here, we do see 2 peaks from the correlation result, and all of the previous frame they are just below the threshold, which is not recognizable by the RX. So we can say that emulated CGS can be detected from the emulated payload. And then before we say that we need to detect the packet start correctly, right? So the Wi-Fi system detects the packet start with detecting the location of LTF. So right here, we need to evaluate this part. So we need to have the emulated LTF to be detected rather than the previous one. So right here, as you can see, because of the existence of the shift, the previous standard preamble is becoming valid, and the Wi-Fi could be detecting the packet start before the CGS. So these 2 results basically shows that the StarLego can emulate the time domain signal with relatively high accuracy. So right here, we have shown our prelim result. This is what we have. There are still some problems. So this is the following problems I'm going to discuss. So first is computational overhead. We all know that we need to convert the time domain, a desired signal, into our MAC payload we want to do. But usually we just do it convert serially. But when the frame is very, very long, there will be an issue that the conversion time is going to be high. So we take 2 signals. We separate this desired signal into 2 categories. The first is the predefined signals. So like LTF or STF in the Wi-Fi center, those are predefined and short. That we can know that we can pre-convert them and pre-store them into the device to save the computational time. And for the rest, for the emulated data payload, it have to be real time, and then we don't know exactly what we're transmitting. So in order to save time, we can convert them parallelly by segment them into individual smaller parts and convert them parallelly, and then we can save much time during this conversion. And the second one is the possible distortion emulation. So we all know that this concentration point is discrete. So it cannot be like I cover every part of the concentration point. So there's a chance that the design point is not matching any of the concentration that we can emulate. So we take a BPSK signal, BPSK concentration example here. We choose BPSK because it's used in the common Wi-Fi preamble, so it's very representative. So right here we can see that even with 2 times 64 QAM, we still have a little bit. Still have a deviation from the desired signal to the desired concentration to the emulated concentration. But if we increase to 3 times, this D2 is actually shrinking, but it's still not exactly match. So in order to reduce such distortion, we can use higher order modulation or use more TX antennas to reduce. And then the third part is, because as we said before, StarLego is built on MIMO. So you may ask, if our device don't have MIMO, there's a possibility that we can implement StarLego into the device that don't have MIMO. We just use multiple individual transmitters, and then when they are mixing, when the signal is mixing in the air, they will be able to still create a similar pattern as the emulation we addressed before. But the key here is if we use multiple devices, because they don't share the same clock between them, the timing will be crucial. As you can imagine, that if we can increase the number of devices, there's a possibility that we can emulate more wider channel bandwidth, like 40 megahertz or 160 megahertz. There's a possibility. So this is what we have for our StarLego. This is a very promising result we currently have to bridge the gap between the old devices and new devices. Although it's in its infant stage, there's still a lot of problem to be addressed, but it did show some promising for the future research. And yeah, that's it. And thank you very much. And I would like to take some questions.